Okay, so if you go on the slide, or actually, do you mind sharing your screen? Let me stop sharing mine. I'll have you share yours because it's easier and I can guide you through it. And your screen looks different than mine, so you'll be able to sit there and see. Bernice, you said you don't mind sharing your screen? Or you do mind sharing your screen?
Oh, I'm using a phone right now.
Okay, so if you go to the canvas shell, do you see that image that looks like people together, like a person in front and a person in back? Click on that. Okay, so that tells you all, oh, your groups didn't show up. Okay, so I need to figure out why your group is not showing up. Give me 1 second. That is really odd because you should, that's where you would actually figure out the group that you're in. And I don't know why yours hasn't shown up. Give me 1 second.
So the group, isn't it the discussion one? Group 9? Is
No, it's not your discussion group.
because I don't have a group, like I just have that one.
Okay.
I thought that was my group for the project. Is it the one that says the topic of your group?
Yeah, so if you go ahead and share, yeah, there we go. There we go. So perfect. So right there, it says balancing chemical equations. So if you hit the people in your group, so that tells you everybody in your group. Okay. So if you go down to the email box, go ahead and click on it. So if you go to select write a message, and then go to select course, go down to groups. So then you can select your groups, and then you can select all of the people in your group, and you can add an email and introduce yourself to your group. Okay, so let's go ahead and there was a question about the lab. So I'll be making a spot for that lab, the last lab. I'll be putting it up hopefully by the end of the day. So you should be able to upload it. Have you guys already done the lab? You guys are really on top of things. Okay. Was it pretty simple? Wasn't too hard?
What was it? Sorry.
I said, have you guys done the lab? Last week's lab?
No, I haven't.
Okay, so we want to make sure I'll put up the actual instructions and then also a spot to actually upload it. So you'll be able to get that done. This week's lab, we'll be dealing with, let's see, so we've done electron configuration. So it'll be molecular geometry is what we're going to be doing. So we'll be talking about it, and I'll put up the lab for it today. I'll make sure that it's available. It should be available already, but I need to make sure that it's open for you guys. So you guys will have an idea what you're doing. And you guys are going to be using the cutouts of the different elements. So the one that says like oxygen and carbon and all of those guys. So we'll be using those to sit there and do that lab. So If you want to, you can actually go ahead and get started at cutting those guys out because it makes the lab go a lot faster. So you guys know what I'm talking about, the ones that came in your packet. Your lab kit.
Yeah.
Okay. Okay, so let's go ahead and we'll go ahead and get started. Share my screen. And so. Okay, so we're going to start with Lewis dot structures. Okay, so the thing about Lewis dot structures, the first thing that we always want to do is count the number of valence electrons. Okay, and if it's an ion, we want to adjust for an ion. So let's say, for instance, if I have fluorine, the fluorine ion, which is adding 1 electron. Okay, so if we do the Lewis dot structure, we want to know the valence electrons that fluorine has. So do you guys remember what valence electrons are? So quick reminder, our valence electrons are the electrons that are going to be able to be utilized for bonding. Okay, so if we go to P table, I'm going to, 1 second. Okay, we go to P table. And you guys see that fluorine is located right here. So if we count what we call the S and the P orbitals, so that would be from here to here in the second period, because fluorine is in the second period. So that's 1, 2, 3, 4, 5, 6, 7. So fluorine has 7 valence electrons, and it needs 1 more to be like neon so that its octet is full. So as I said, we have F minus, right? Which means that we're giving it that 1 extra electron. So in that case, we would draw fluorine with, fluorine has 7 dots on its own. And because we put that extra electron there, it gives us a negative charge. So it has 1 more dot. So in that case, its octet will be full. We put this guy in brackets, and we put the charge on it. Okay, to let us know that we added 1 extra electron. Okay, so if I was doing silicone, so then I just count 1, different color, 1, 2, 3, 4. So silicone has 4 valence electrons. Oops. So in this case, because it's not an ion, it's just an element, we would just put the 4 dots around it. Okay? And we know that it has 4 valence electrons. So that means that it has 4 electrons that it could use for bonding or to take or to give, you know. So it has those 4 electrons to give. And it would like to try to get to its octet. So it wants to be like argon, right? So it's going to try to get to the point where it's like argon. Are you guys with me so far? Okay, so We can see that I can do it. Let's see if you guys can do it. So can you tell me the number of valence electrons around arsenic? Okay. Let me erase all the other stuff. Okay, that's correct. Arsenic has 5 valence electrons around it. So we count the S and the P. So that's 1, 2, that's 3, 4, 5. So then we would draw it. The Lewis dot structure for arsenic would be AS 1, 2, 3, 4, 5. So AS with 5 dots around it. Pretty simple, not too hard. Now, the Lewis dot structure helps us.
I have a question.
Yes.
Do the transitional metals not count as valence electrons?
So, yes, the transitional metals, we do not count the transitional metals as valence electrons because let me kind of explain to you why, right?
Okay.
Now, don't get me wrong, they have their own valence electrons, right? But we don't count those as our valence electrons because they're not in the outer shell. So when we're looking at this is called group 1, group 2, group 13 through 18, right? So those guys are considered the main group. So if we're looking at elements that are in the main group, these guys are completely full, right? So the orbital or the subshell that would be right before it would be completely full. Like, so for instance, this guy is 3D, right? So if we get to arsenic, this guy is completely full. Now, the rule of thumb is that it doesn't like to use that, right? It won't use any of the electrons in there unless it absolutely must use it, right? So it's going to try to keep that. Once it's completely full, it's not going to want to mess with it. So it's not going to want to mess with the 3D, right? It only wants to mess with the ones that are in the outer shell. So this guy would be the 4S, and this guy would be the 4P. So that is a higher level, that's a higher period than the 3 period. So it's going to pull from that higher period first before it starts to pull from the 3. Okay, so it's going to use up the ones that are in the 4th period before it uses the ones that are in the 3rd period. Okay, do you understand?
Yeah. So wait, would we ever build a Lewis structure for one of those metals?
Can you please?
Sorry, would we ever build a Lewis structure for one of those metals or no?
No, so typically you don't build Lewis structures for the transitional metals. And the reason why is because, well, for a couple of reasons. One of the things is that the transitional metals has the ability of having multiple charges associated with it. So it uses its electrons a little bit differently. And so it could have multiple charges compared to, let's say, the group 1 or group 2 metals, right? These metals here. Transitional metals can be, and part of the reason why they're called transition means change. They're capable of having different charges associated with them. And so they don't really obey the octet rule the way that group 1 metals and group 2 metal does, or the non-metals or the metalloids do. Okay, does that make sense?
Yeah, thank you.
So they're kind of exceptions. But you're asking all the right questions. It's good. It makes me feel good that you're kind of, asking those questions, because those are some of the questions I remember when I was taking a class. I'm like, I didn't quite get that. And I noticed that although we talk about the transitional metals, we often will not pay as much attention to them. That's kind of changed, with your class, and because we know a lot more about them than we did when I was actually taking the course. So, but we'll talk more about those in a minute. Okay, so let's do the Lewis dot structure for selenium. Okay, do you guys know you can write on my screen, right? If you, long as you don't have a Chromebook, what you can do is you go to annotate, you click annotate, and then it allows you to write on the screen. So does any of you guys want to write on my screen and show me the Lewis structure for selenium? Any volunteers? Okay, anybody want to tell me how to do it? Okay, well, can you tell me how many valence electrons would selenium? Ah, yes. Okay, there would be 6 valence electrons. So Se, 1, 2, 3, 4, 5, 6. Now, you'll notice kind of like I have a little bit of a pattern going on. I put them in groups of 2, right, if I can. Or I put like 1, 1, 1, 1. That's kind of like how the electrons fill their orbits, right? So if they can, they want to be paired up, but they prefer to be individual first, okay? So let's say, for instance, we have aluminum, Al. So what'll happen is that it'll put electron in, let's say, the s orbital. So you could do it like this, as if it's paired up, and then you have the 1 there, or you have the option of just doing it Al dot dot dot, okay? Either one is fine, okay? And so that just basically means that I'm able to sit there and make bonds with that aluminum, or I can take those electrons from that aluminum, okay? Does that make sense? Okay, so when we talk about Lewis dot structures of compounds, so the first thing that we want to do is count all of the valence electrons for each of the different elements, okay? So if we talk about ammonia, so we know that nitrogen has how many valence electrons? It has 5. And each hydrogen, we have 3 hydrogens, has how many valence electrons? 1, that's correct. So that is a total of 3 plus 5. So we have a total of 8 electrons to work with. So the first thing I would do is I would put my valence electrons around the nitrogen that it has, and then I'd put the ones around the hydrogen. Okay, so then we want to set it up. We want to figure out a way so that we can get 8 electrons around every element except for hydrogen or helium. Hydrogen only wants to have 2 electrons around it because it wants to be like helium. Okay, so hydrogen wants to have 2 valence electrons. Okay, so we want to, and we've got to remember that the electrons are movable, right? So they can move around. Okay, so if we share a bond here, so that represents, that is a bond, it represents 2 electrons. We share a bond here. And then we're going to move this electron over to here. And that means I'm going to erase this one here. And we share a bond here. So we have a total of 8 electrons to work with. So that's 2, that's 4, that's 6, that's 8. That's all 8 electrons that are needed. Now, if we count what's around the nitrogen, that's 2, 4, 6, 8 around the nitrogen. So nitrogen reaches its octet. So nitrogen is happy. Hydrogen only wants 2 electrons around it. So that's 2 around this hydrogen. That's 2 around this hydrogen. That's 2 around this hydrogen. So hydrogen is happy. Okay. And so everybody's happy in this regard. You guys see that? Okay, good. Okay, so let's say if we had water, H2O. Now, the question is, how do we determine which element is going to be the center element? Right? The way that we determine that is by looking at the electronegativity. The element that has the strongest electronegativity is never going to be the center atom. Okay, the one that has the weakest electronegativity is going to be the center atom. I don't know if I shared this analogy with you guys last week, but so I have two sisters, right? I'm the oldest, and one of my sisters is the youngest, right? And so when we went on road trips growing up, we used to have to decide who's going to sit in the middle. So how do you think we decided who sat in the middle? The little, yes, that's right. The little one did, right? Since I'm the oldest, I'm stronger than my little sister. I would always push her in the middle. My middle sister would always push my other sister, make sure she got in the middle. So regardless of what my little sister did, she would always have to sit in the middle because she was weaker than both of us, right? And so that's exactly what happens in terms of the atoms in a compound. So the one that has the weakest electronegativity always gets put in the middle. They're often also the ones that are capable of having more attachments. They can make more bonds. So often you will have carbon being in the middle, okay? So that applies in almost all cases, except when you have hydrogen. Hydrogen always has to be at the end because it only forms one bond, okay? It can't have two bonds, it only have one bond. So hydrogen will always be at the end. The other thing is that the halides, so group 17, they also like to be at the end. They often will have a stronger electronegativity, but they also like to be at the very end. And so they typically will be at the end as well because they only want to form one bond, okay? So who's going to be the center atom in the case of H2O? That's right, the O. How many valence electrons does the O have? 6. So that's 2, that's 4, and that's 6. Okay. So hydrogen has how many valence electrons? 1. Okay. And 1. So that's a total of 8 electrons again that we're working with. So we'll have these 2 electrons be sharing. So then we'll move this guy. Okay, so then our Lewis dot structure is going to look like this. Okay, you guys see that? Simple. Any questions on it? And if you don't see it, ask questions. This is a great opportunity to ask questions. Okay, so let's see if we can do something a little more challenging. Okay, so what happens if we have a polyatomic ion? So did you guys print out this stuff, the chemical packet and stuff for the exam? And if you did that, you have a table that says polyatomic ions on it. Okay, good. So if we have SO4, and that's 2 minus. Let's do SO3, 2 minus. Then we'll do SO4, 2 minus. Okay. Okay, so this is a polyatomic ion. So it forms a covalent bond to make this ion. Okay, so how many total valence electrons does this compound have? How many does the sulfur have? And how many does each of the oxygen have? Valence electrons. So let's start with the sulfur. Sulfur has how many valence electrons? 6, that's right. Okay, so sulfur has 6. And each of the each of the oxygens have 6. So we'll go O, and it's 3. So 6 times 3. And then this here means that we're adding 2 more electrons. Okay, so if we add this together, we have a total of, 18, 24, 26 electrons that we're working with. Okay, so we have a total of 26 electrons. Who's going to be in the middle? Sulfur, that's right. Sulfur has a lower electronegativity than oxygen, so then sulfur is going to be put in the middle. So we said it has 6, 1, 2, 3, 4, 5, 6. And we have 2 extra electrons that are being added onto it. 1, 2. And I like to put those on the center atom because the center atom is kind of like the one that's connecting everything. So we want to make sure that we have it there so then we can just move the electrons as needed. Does that make sense? Okay. Okay, so then each of the oxygen, it has 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And 1, 2, 3, 4, 5, 6. Okay, so if we're obeying the octet rule, we're going to have a bond here. We're going to have a bond here. Oops. And we're going to have a bond here. Okay, so now let's count how many is around each of the different elements. So that's 2, that's 4, that's 6, that's 8 around sulfur. That's 2, that's 4, that's 6, that's 8 around this oxygen. That's 2, that's 4, that's 6, that's 8 around this oxygen. That's 2, that's 4, that's 6, that's 8 around this oxygen. And then the last thing that we want to do is put it in brackets and put the charge on it. Okay, because it's an ion, just to remind us that it is an ion. Okay, you guys see that? Yes, no, maybe? Okay.
Yes, I have another question. So sometimes in the homework, the bonds are double. Why is that?
That means that they needed to share a total of 4 electrons to either reach its octet, or if it needed to reach what we call a formal charge. We'll talk about the formal charge here in a minute, because certain compounds will allow that center atom to kind of break the octet rule, and so that it would be more stable. And so formal charges allows us to determine how stable that compound is. So if you get your formal charge, so it adds up so that it's almost completely 0 for each of the different elements, it's usually a more stable compound than if it has a plus or minus charge on one of the elements compared to the other. And I'll show you an example of that here with this particular compound, okay?
Mhm.
Okay. So we'll talk about formal charges since we've brought it up. And you guys will see in the homework that you guys may have to figure out what the formal charge is. So let me write that down, formal charge. So the way that we determine a formal charge of each of the element is, and again, the formal charges kind of lets us know whether or not a compound is going to be stable, right? And the goal is to get for each element, you want to get the formal charge to be 0 for each of the different elements that are in that compound. That would be the ultimate goal. Now, sometimes you can't get there. So then you want it to have it as close to 0 as you can possibly get it. The further away that you are from 0, the less stable that compound is, okay? So the way that you calculate your formal charges is, it's the number of valence electrons. So it's valence electrons minus the number of bonds minus the number of lone pairs. Okay, so now let me show you, we'll start off with this oxygen here. Okay, so this oxygen has how many valence electrons? Call this O1. So I'll put a 1 here. Put a 1 here, I'll put a 2 here, I'll put a 3 here. Okay. Now, in theory, they should all be exactly the same. So how many valence electrons? You said 6, that's right. So it has 6 valence electrons. Okay, how many bonds are between the oxygen and the sulfur? Not each of the oxygen, just we're looking at the very first oxygen. So you have to do each one independently. Now, that's right, 1. We have 1 bond. It's sharing 2 electrons, but it's 1 bond. Okay. And then how many lone pairs? So this is a pair, this is a pair, and this is a pair. How many lone pairs does the oxygen have? So that's 1, that's 2, that's 3 lone pairs, okay? Okay, so if we look at this value would have a +2 charge associated with it. All right, hold on. Sorry, lone pair electrons. So how many lone pair electrons that we have? That's what this should be, my bad. So it's lone pair electrons. So that's 2, that's 4, that's 6. So then that would be a -1 charge associated with that oxygen. Okay, now the other oxygen, it's going to have exactly the same thing. So that's O2. It's going to be 6 minus 1 minus 6, -1. And then this oxygen, that's O3. So that's going to be 6 minus 1 minus 6. And that's also going to be a -1. Okay, now let's look at the sulfur. So the sulfur has 6 valence electrons. It has 3 bonds, and it has 2 lone pair electrons. So then that gives it a 1 or a +1. Okay, so if we added all these together, we would get the charge on the total compound. So that's +1, -1, -1, -1, which would be a -2, which is exactly what we got for the charge. Okay, now each of these they're close to 0, but they're not 0, right? And if there's any way that we could get them to 0, it would be even better, right? So the way that we sit there and we try to accomplish that is by making, in some cases, a double bond, and then also allowing some of the guys to break the octet rule. Okay, now we'll talk about those that are going to be able to break the octet rule. This compound here is going to be one of those compounds that are able to break the octet rule, but let me kind of get to that part. Okay, does that make sense so far? If not, don't worry about it. We'll come back to it. And then after you've gotten a little bit more stuff under your belt, it may make a little bit more sense. Okay. Okay, let's do one more because you were talking particularly about a double bond. So let's say we have, we'll do 2 different ones. So we're going to do N2 and we're going to do CO2. Okay, so how many valence electrons does nitrogen have? It has 5. So we have 2. So we have a total of 10 valence electrons that we're working with. So 5 times 2. So we have 10 valence electrons. So let's go 1, 2, 1, 2, 3. 1, 2, 1, 2, 3. Okay, so we need to figure out a way of using these electrons so that each nitrogen has 8 around it. Okay, so how many electrons are going to have to be shared for each of them to have 8 electrons around it? Okay, so if you said 2, so you're saying that we have to have 2 here, so that would be a double bond. Okay, so right, 1, 2, oops, no, that isn't right, hold on, got carried away. That's too many electrons. Okay, so if we did that, that'll be 2, 4, 6, 8, 10. That's the 10 electrons that we have. Now that will be 2, 4, 6 around this nitrogen. That's 2, 4, 6, 8 around this nitrogen. Would that work? Are they both happy? Do they both have 8 around them? Okay, so what about if we add one more set of electrons between them? So we make it a triple bond. So that's 2, 4, 6, 8 around this nitrogen. That's 2, 4, 6, 8 around this nitrogen. And we have 2, 4, 6, 8, 10 electrons that we were working with. So does that work? Are both of them happy? Okay, so this is an example of we have to share a total of 6 electrons. 2, 4, 6 electrons have to be shared between the 2 nitrogens to sit there and make it so it reaches this octet. So a bond is the sharing between 2 electrons, right? So that represents a bond. So this guy would be called a triple bond because we're sharing 3 bonds, okay? Does that make sense? Thank you. Okay, so let's do carbon dioxide. So who's going to be in the middle? So here's just a general rule of thumb. Carbon likes to be in the middle, okay? So it's able to hold or attach itself to 4 different things. So it prefers to be in the middle, okay? So we're going to put carbon in the middle. And we know that carbon has how many valence electrons? 4, that's right. So we'll go 2 here, 2 here. So, and then each of the oxygen has how many valence electrons? 6, that's right. So 2 times 6. So that's 12, that's 16. So that's 16 total valence electrons that we're working with. So let's go ahead and put our 6 around the oxygens. Can you guys see my dots, or are they too thin? Okay. Okay, so how many bonds should we have between each of the carbons and the oxygens? So that everybody reaches its octet. Two, that's right. So we should have 2 bonds. So that'll be a total of 4 electrons that are going to be shared between the 2. Okay, so let's count the total number of valence electrons. So that's 2, that's 4, that's 6, that's 8, that's 10, that's 12, that's 14, that's 16. We got them all accounted for. So let's see if everybody reaches this octet. So that's 2, that's 4, that's 6, that's 8. Around this oxygen, that's 2, that's 4, that's 6, that's 8. Around this carbon, that's 2, that's 4, that's 6, that's 8. Around this oxygen. Okay, everybody happy? Okay, good. Okay, so let's go ahead and work on the next one. So draw the Lewis diagram for the hydrogen carbonate ion, HCO minus, I say HCO3 minus, okay? So who's gonna be the center atom? Is it going to be oxygen? Now we have hydrogen, carbon. That's right. Carbon is always going to want to be in the center. So we have carbon in the center. And carbon has how many valence electrons? If I remember correctly, it was 4. Hydrogen has how many? And each of the oxygens has, if I remember correctly, 6. Okay, now what does this mean? Yep, that's right. We're adding 1 more. So then that is 1, that's 5, that's 18, so that's 23, 24. So we have 24 electrons to work with. So let's go ahead and put 1, 2, 3, 4 around the carbon. We have that one extra. So we're just going to go ahead and put that one extra. And then we have oxygens. There's 1, 2, 3, 4, 5, 6. There's 1, 2, 3, 4, 5, 6. There's 1, 2, 3, 4, 5, 6. And then we have that one hydrogen. Okay. So if we manipulate this, right, we could have one bond here. We could have one bond here. We could have one bond here. Okay. Now, this is a problem though, because we don't have enough electrons to have a bond so that this guy would reach its octet. Even if we brought both of these guys around, this guy would not reach its octet. We'd also have too many around carbon. Okay. So then that would suggest to me, I'm like, oh, okay. So regardless of how I manipulate it, I can put a double bond here. I'm still not going to be able to reach my octet because I won't have 8 around this one. So that would suggest to me that I need to do something a little bit different, right? And what I need to do in this regard is maybe this hydrogen doesn't go around this carbon. Maybe it goes around one of the oxygens. And that's exactly what happens. So let's go ahead. We're going to put these guys here. And I'm going to put those here. Circle that in a different color. Okay. So now I have and I'll put that H here. Okay. So if I do that counting again, that's 2, that's 4, that's 6, that's 8, that's 10, that's 12, that's 14, that's 16, that's 18, that's 20, that's 22, that's 24. That's all 24. Now, is everybody happy this way? So hydrogen has 2 around it, so hydrogen is good. Oxygen has 8 around it, so this oxygen is good. This oxygen has 8 around it, so this oxygen is good. And this oxygen has 8 around it, so this oxygen is good. But carbon only has 6 around it. So we need to find a way of making it so that carbon has 8 around it. What can I do? Any suggestions? Do I just cry? I can't get it. Throw in the towel. No, we can't just cry and say I can't get it. So we can still move electrons, right? So what if I move these 2 electrons on top of this oxygen here? Or on top of this oxygen, next to this oxygen. And I move those and share those. Would that give me my 8 around the carbon? Yes, it would, right? So let's go ahead and do that. Okay, so now let's count the number of electrons around everyone. So that's 2, that's 4, that's 6, that's 8 around this oxygen. That's 2, that's 4, that's 6, that's 8 around the carbon. That's 2, that's 4, that's 6, that's 8 around this oxygen. That's 2, that's 4, that's 6, that's 8 around this oxygen. Okay, and then the last thing that we want to do is put in brackets and put that negative charge on. Okay, Do you guys see that? I like that. Oh, it makes sense. Okay. Do you guys get that? See how it works? And so the goal, again, if we can reach our octet, we want to try to reach our octet. Now, there are going to be exceptions that we can't reach our octet, or we'll break that octet rule. We'll talk about those here in a second, okay? Okay. Okay, so this kind of brings us what we call a resonance structure. So you see this guy that we've just drawn? I'm going to actually go back so we can actually see my screen without. Okay, so a resonance structure is a structure where the electrons are basically moving from one atom to another atom that is exactly the same. So for instance, the resonance structure for this guy would be okay, so do you guys see the difference between this structure and that structure? So all we did, we basically moved where that double bond was at, okay? So that is considered a resonance structure. So in reality, what happens is that both of these structures can exist at the same time. It could be on this and that one because it's always constantly moving. The electrons are constantly moving, so you may end up having one of those structures existing at one point, and at the very next point, you may have the other structure existing. So these guys would be called resonant structures to each other, right? And so we usually just draw like an arrow between the two to represent these are two resonant structures of each other. Just the fact that we know that electrons are always moving, okay? And so you'll have electrons that will be moving that will be forming those resonant structures that exist. Does that make sense? Okay. Okay, oops, I got carried away. Okay, so, and as I said, these guys, they will be equivalent structures because they both will actually exist at any given point, okay? Now, we don't want to mistake resonant structures for isomers, right? So for instance, if we have, let's see, C2H3O2. Okay, so we have this molecule here, right? So we know that in this case, carbon is going to be the center atoms. So carbon is always going to end up being in the center. So we have C. And I'm going to draw this out for you guys so you guys can see it. It's a little more complicated since it's a much bigger structure, right? Sorry, it should be, let me fix this. That should be a 4. Okay. So this here would be one of those structures, right? You guys can kind of see that, how that works. Right? And I should put my Lewis dots on this as well. Okay, so this is an example of one structure. We have, and then we have this guy. Okay, so that's 2, 4, 6, 8, 10, 12, 14, 16, 18. 2, 4, 6, 8, 10, 12, 16, 18. 2, 4, 2, 6, 8, 18, 20, 22, 24. I'm missing a bond here. Four, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Okay, there we go. Two, 4 hydrogens. Give me 1 second while I fix this. Two, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Okay, so if we look at these two structures, these guys are called isomers of each other. So they have the same number of let's say, of all of the elements. So they have the same chemical formula, but they have different structures. This is a single bond. This is a single bond. There's a double bond here. There's a double bond here, single bond between it. So these guys, they are two different chemical compounds, but they behave differently. So they're two compounds that have the same molecular formula, but they have different structures, okay? And they're gonna have differences between their physical and chemical properties, okay? Does that make sense? And you guys can kind of see that. Okay, so again, those guys are called isomers. Iso meaning same, mers meaning unit. So basically, it's the same unit. Okay. Okay, so when we talk about resonance structures, these are examples of resonance structures where we're actually just moving the double bond from one oxygen to another oxygen. Okay. And so these guys are three independent resonance structures of each other. Okay, so then that brings us to the electron pair geometry. Okay, so electron pair geometry is the geometry that is going to be resulting from electrons repulsing from each other. So how many of you guys have siblings? You guys all said that you had siblings. Is that correct? You have brothers and sisters? Okay. So as kids, did you or your brother or sisters try to sit right next to you just to kind of annoy you, to get on your nerve? They like really, really close to you, right? Walked into your space. Did they ever do that to you? So they still do. Okay. Okay. So now, so with electrons, this is the same thing that happens. So two electrons, they don't want to be right next to each other, right? Or two electron pairs, they don't want to be right next to each other. they want to try to be as far away from each other as possible. Okay, so they're going to arrange themselves so that that happens, right? Because we get really annoyed if somebody comes into our space. The electrons are exactly the same way. They don't want to sit there and have anybody in their space, so they get pretty annoyed by it. So electron pair geometry is a result of them trying to get as far away from each other as possible. And that's because they repel each other. Kind of like your sibling. You guys kind of repel each other, right? And so if you do that to your sibling, they get annoyed and like, get away from me, and they push you away, right? So that's essentially what's going to be happening with the electron pairs, okay? The electron pair angle is going to be the angle of how far they are away from each other when they're connected to the center atom, okay? And then a tetrahedron is basically, it's a four-sided shape, okay? So that it actually has essentially four faces to it, okay? So let me show you all of these things so it'll all start making a little more sense, right? Okay. So if we have electron pair here and electron pair here, this is our center atom. So this sticks represents the electron pair. So those electron pairs are going to try to be as far away from each other as possible. So it's going to be 180 degrees. So that would be our electron pair angle, repulsion angle, right? So then it's going to be 180 degrees away from each other, okay? Because that would be the furthest distance that they can get away from each other. If I have three electron pairs, 1, 2, 3, then it's going to be 120, 120, 120, because we form a circle. A circle is 360 total degrees. So if we just divide that by 3, each one will be 120. Okay, and then in the case of if we have 4 electron pairs, so for it to be furthest away as possible, these guys are going to be at an angle of 109.5 away from each other. So every one of these angles will be 109.5 degrees away from each other. Now, this shape here we would call linear, because the electron pairs are linear. They'll be in the same line as each other since they're 180 degrees. Now, this shape would be called trigonal planar. Because they're all in the same plane, kind of like a flat sheet of paper, but they have 3 attachments to them. So that's 1, 2, 3. So that's tri meaning 3. Okay, so that's why we get trigonal planar. Okay, and then this last shape is called tetrahedral. Tetra meaning 4, and then hedral meaning, when we were talking about each of them having planes, like 4 faces. So this guy has like 4 faces to it. So when you have 4 attachments, it's going to form a tetrahedral shape. Okay? Are you with me? Yes, no, maybe, sort of. Okay? So are there questions? Or is there something that you guys don't quite get? Okay. Okay, so as soon as there are questions popping up, feel free to ask them, okay? Okay, so here we're going to be basically using balloons to show us the different electron pair geometry. So again, we're talking about electron density, meaning that the electron is always moving, so it's circling the nucleus and everything like that. So that's going to represent the electron density. So if we look at, we have 2 things that are connected to each other, right? So this here represents our center atom. This will be an electron pair here. This will be electron pair here. So this guy will be linear to each other, okay? So, and the bond angle is going to be 180 degrees. This here is showing us our trigonal planar. So they're flat. And then the angle between each of these is going to be 120 degrees. This one here is showing our tetrahedral, right? So that's 1, 2, 3, 4. 4 things attached. The angle between these guys is going to be 109.5 degrees. Okay. Questions? Let me clear this. Okay. So if you guys have any questions, feel free to stop me. Okay, so we have what we call the electron pair geometry, right? So that's looking at electron pairs, and it's looking at attachment of atoms to it as well. So we take both of those in consideration. Where the molecular geometry is kind of looking at what's attached, and then also how the lone pairs will kind of affect the shape, because the lone pairs are going to cause the shape to be altered a little bit, right? If you have attachments of atoms and lone pairs, it's going to kind of push things, right? Because of that repulsion theory. So those lone pairs will cause things to be pushed a little bit more than what we expect them to be, okay? So let me kind of go through and explain that, okay? Using a diagram here. Okay, so if we have 2 lone pairs attached to a center atom, this guy's going to be forming a linear structure. If we have 2 other atoms attached to the center atom, it's also going to be forming a linear structure, okay? So the electron pair geometry for this is going to be a linear geometry, and then the molecular geometry is also going to be linear, okay? Because it's just going to be a straight line, okay? So an example of this is when we have the bond between beryllium and fluoride. Okay, so beryllium fluoride will actually form a linear structure. Okay, so where beryllium is going to be that center atom, and then each of these are going to be the fluoride. So its molecular geometry is going to be linear, and its electron pair geometry is also going to be linear. Okay, so we talked about the trigonal planar. So if we have 3 electron pairs attached to the center atom, then it's going to form a trigonal planar. That's going to be the electron pair geometry. So if I have 3 atoms attached to a center atom, then that's 1, 2, 3, and there's no lone pairs. So then this guy is also going to be trigonal planar. So the angle between these are going to be 120 degrees. Okay, so an example of this is boron fluoride. So boron being the center atom, and fluoride is attached to each one, okay? So this guy would also be trigonal planar, and its electron pair geometry would also be trigonal planar. Okay, so if we have, again, 3 attachments, or 3 lone pairs to a center atom, that guy is going to be trigonal planar. Okay, so in this case, what we've done, we formed a double bond, and we have a lone pair on top, and then we have a single bond here. So we have 1, 2, technically 3 things attached because we have that lone pair. So its electron pair geometry is going to be trigonal planar, but its molecular geometry is going to be bent because we're not going to see that lone pair. And so when we talk about molecular geometry, we're talking about what we're going to be seeing visually. So we see just this bent structure because we don't see those lone pair being shaped. Even though that they affect the 2 other atoms, it causes those atoms to be bent, right? And so it has that bent structure, okay? So an example of that is sulfur dioxide. Okay, so if we have 4 lone pairs attached to a center atom, we call that tetrahedral. So the electron pair geometry is going to be tetrahedral. So each of the angles is going to be 109.5. So if we have 4 things attached to a center atom, 4 atoms attached to a center atom, its molecular geometry is going to be tetrahedral. Its electron pair geometry is going to be tetrahedral, and its molecular geometry is going to be tetrahedral. Okay, so an example of that is methane, where you have carbon is going to be their center atoms, and it has 4 hydrogens attached to it. Okay, so if we have 4 attachments, right? But one of those attachments is a lone pair, and 3 of them are atoms. So this guy here, its molecular geometry is going to change, but its electron pair geometry is still going to be the same. It's going to be tetrahedral because it has 4 attachments. But its molecular geometry, because we don't see those lone pairs, they're invisible to us, it looks what we call trigonal pyramidal. It actually will push those, it'll push the hydrogens down a little bit, so it looks like a pyramid structure. So it looks like we have a pyramid structure forming. So then that's the reason why we call it trigonal pyramidal. Trigonal meaning 3. So we see the 3 atoms being attached. And then pyramidal, it looks like a pyramid. Okay. So an example of that is ammonia, sorry. Our last example is, again, where we have technically 4 attachments. So 2 of these attachments will be lone pairs. 2 will be the hydrogen atoms, like in the case of water. And in this case, again, those lone pairs are not going to be visible to us. So our structure is going to look bent or angular. Again, so it's just going to look like a little boomerang in this case, right? Or rabbit ears, okay? So again, it's electron pair geometry, because electron pairs shows us everything. So we see those lone pairs as well as the 2 atoms that are attached. So that would be tetrahedral, but the molecular geometry would be bent or angular. Okay, are you guys with me so far? Okay, good. Okay, so all 3 cases, the electron pair geometry is going to be tetrahedral. So you have 4 things attached to each of those. Okay, so but the molecular geometry, so the electron pair geometry is going to be tetrahedral, but the molecular geometry is going to change. In the case of the methane, methane is going to be tetrahedral. It's going to be exactly the same thing. In the case of the ammonia, you're going to just see the 3 hydrogens attached. So this guy is going to be trigonal planar. And then in the case of water, this guy is going to be bent. Okay. Okay, so sometimes to get our structures right, and so that we can kind of see what's happening with our structure, since it's a 3-dimensional structure, what we have to do is sometimes we have to use what we call the wedge dash diagram. So the wedge dash diagram is basically allowing us to determine whether something is coming out towards us, something is towards the back of the element, and something is up, and something towards the side. So let me show you what that's going to look like. Oops. Okay, so here, this is an example of the wedge dash diagram. So we know that we have 2 lone pairs that are going to be sitting up top here, right? So that's going to be towards our top. So the wedge, this here represents the wedge. So this is coming out towards us. The dash, which looks like a Wi-Fi signal, that's going to be behind us. So that represents one that's coming towards us, and then the one that's coming behind us, okay? And then this is the one that would be in the same plane as the nitrogen itself. So one in front of it, one behind it, and one next to it, okay? And then you have the lone pair that's on top. Can you guys see that? So if we're doing NH3, right? Same concept. where we have our lone pair, our nitrogen. This would be one hydrogen. And then we'd have a hydrogen going behind. And then we'd have a hydrogen in the same plane. If we have multiple bonds, so like in the case of a double bond or a triple bond, Vesper rule is still going to apply. So again, those atoms are still going to try to get as far away from each other as possible, right? And so they're not going to affect. So that double bond and a triple bond isn't going to affect that attachment trying to be away from each other, okay? So like for instance, we have tetrafluorothylene. Now in the case of the tetrafluorothylene, there's going to be a double bond between, there we go. Oops. Okay, so in this case, we still have three things attached. So this double bond doesn't affect the shape of it. It's still going to try to be as far away as possible from each other. So if we take a look at this, that's three attachments. So then this guy, it's molecular geometry. It's going to be Trigonal Planar. And it's electron pair geometry. It's also going to be Trigonal Planar. Okay, so for that carbon. So, and you've got to look at each center atom independently. So when we talk about that geometry, we're talking about the center atom based upon that center atom. Okay, you guys get that? Okay, so the wedge dash for this particular molecule would be, again, they're going to be planar, so it's going to be flat. So in this case, you won't have anything coming out towards you or back towards you. It's all going to be in the same plane. Okay. Okay, let's see. Now let's talk about polarity. So we talked about bond polarity in the last chapter, right? So when we talk about bond polarity versus molecular polarity. So a polar molecule basically means that we have something that has a positive charge and a negative charge on another pole, okay? So like if we take a look at water. Okay, bond-wise, if we look at the bond between hydrogen and oxygen, we know that the polarity or the bond polarity is going to be favoring towards oxygen, meaning that the electrons are going to be moving towards the oxygen, right? So the electron is going to be spending more time around this oxygen in the case of this hydrogen and the oxygen, because the electronegativity of oxygen is greater than that of hydrogen. And that's the same thing that's going to be happening over here, right? So that would be for each of the bonds, right? Now we have to look at the molecule as a whole, because each of them are acting a certain way. They're going to make a field that's going to be associated with the electrical field. So in that case, if we look at the molecule as a whole, it's going to be like adding up each of the ones individually. So in this case, the molecular polarity is going to be towards the oxygen as well as a whole, because both of the hydrogens are moving towards the oxygen. Okay. So how are you guys doing so far? Good, bad, or ugly? Okay. Okay is an acceptable answer. Okay, so now let's take a look at, so we're going to basically look at carbon being the center atom. And we're going to start off with 4 chlorines that are going to be the attachments, okay? I'm going to show you the image. It's a lot easier to see. So the way I like to look at this is kind of like an analogy, right? So in the case of where we have 4 chlorines, right? 4 chlorines means, so we have 4 chlorines attached to that center carbon. Okay, so each of those cases, the bond polarity is going in this direction. The bond polarity is going in this direction. And the bond polarity is going in this direction. And the bond polarity is going in this direction. Okay, so it's basically being pulled away from the carbon. So in this case, let's say you're dating quadruplets. Quadruplets is 4, right? So, and they are like the most handsomest guys, and they're really nice to you. They buy you really nice things. They take really good care of you, right? Now, there's not too much differences between them. They're almost exactly the same. Now, if you had time, you want to spend time with all 4 of them, right? And so in this case, it's kind of like what's happening here with the electrons. The electron wants to spend time here, and wants to spend time here, and wants to spend time here. It wants to spend time there. So this time is being spent equally among them all. So neither of them are going to be favored, right? You guys see that analogy? You see how that works? Okay. So let's do something a little different now. Now, in the case of CHCl3, we have 3 chlorines. Chlorines, the electron is going to be spending more time with the chlorine in this case. And then in the case of the hydrogen, it's not, right? So this is kind of like you have, let's say, 4 brothers, right? three of the brothers, they treat you really good, but one of them is a bum, and he's cheap, and he treats you badly, right? So are you going to want to spend time with him? No, you're not, right? So you're going to want to spend time with the ones that are treating you good, that's giving you all of the good things, they're taking care of you, they make you meals, they, you know, so you're going to want to spend all your time with those. So you're going to share that time among those three and not spend any time with that last one. And so that's kind of like what polarity is. So in that case, the polarity is going to be moving towards the three and away from that one. Okay, because you don't want to spend any time with that one. So then the molecular polarity is going to be moving towards that. Okay, so if we had two of the twins that were horrible, right? They treat you really bad, and then two of them treat you really good. In that case, you want to move towards two that are treating you really good. So your net polarity would be towards that individual. And then in the case of where you have three that were treating you really bad, one that was treating you great, you'd want to move towards that one that's treating you great, and you want to be avoiding the other ones, right? And then if they're all treating you bad, then you don't want to have anything to do with any of them, right? And so then you're not going to waste any of your time with either of them. Does that make sense? Do you guys kind of see that analogy? You see how it works? Okay, so if we looked at the polarity, this guy is nonpolar. This guy would be polar. This guy would be polar. This compound would be polar. And this guy would be nonpolar. Okay, how you doing? So in the case of these two compounds, we've already talked about water, but in the case of carbon dioxide, so in the case of carbon dioxide, we have the polarity moving in this direction, and we have the polarity moving in this direction. So in this case, it's kind of like you have people pulling you on both sides, but they're pulling evenly. So if they're pulling you on both sides, you're not going to move towards one or the other, right? You're going to kind of stay in the middle, right? Because they're same as strength on both sides. So in this case, this guy would be nonpolar. But in this case, in the case of water, because they're both moving towards the oxygen, then the net polarity will be going towards the oxygen. Okay, are you guys getting that? Are there any questions? Okay. Okay, so we're going to change gears a little bit. We're going to talk about organic chemistry. Now, the reason why organic chemistry kind of comes up at this topic is because a lot of the molecular geometry, that concept, and then also the structure, it helps us kind of understand how the structures of organic chemistry is kind of made. So it's kind of like a good time to bring it up. Now, we're going to be talking about some of the definitions in terms of organic chemistry. That term organic, we're often misguided because, you know, the news media has kind of redefined what organic means. When we talk about organic chemistry, we're basically talking about the study, the research, and the application of carbon compounds. Okay. So organic basically means that it has carbon in it. Okay. So organic chemistry, again, is going to be a study of carbon compounds. Inorganic chemistry is the study of all the other things except for hydrocarbons and their derivatives. Okay, now carbonates, cyanides, oxides that have carbon, and then just a few carbon containing compounds will often also be classified as inorganic. Okay, so carbonate will sometimes be called inorganic. Carbon dioxide, inorganic. Okay, carbon monoxide is often considered inorganic. Okay, so but if it's a hydrocarbon, it's going to be considered organic, and any of the derivatives from it. Okay, so now you probably want to know what a hydrocarbon is. So a hydrocarbon is a compound that is made up of only hydrogen and carbon. So I'm going to ask you a question. Maybe. So is this considered organic? No, that's right. This wouldn't be considered organic because this is an oxide of carbon. Okay, how about this? Would that be considered organic? Now, this would actually be considered organic because it has that hydrocarbon base, and this oxygen makes it a derivative of it. So this would be considered an organic compound. Okay, how about okay, how about that guy? Yes, that's right. That would be considered organic. And then how about this guy? Yes. Okay. So now when we talk about a hydrocarbon only has hydrogen and carbon. So which one of these would be a hydrocarbon? Or would all of them be hydrocarbons?
Wait, can you repeat that again?
I said a hydrocarbon only has hydrogen and carbon in it.
Mhm.
And I said, so which one of these would be a hydrocarbon?
Would it be the CHO?
You said this one or this one?
The second one you circled.
You said this one would be?
Mm-hmm.
So does it have only hydrogen and carbon in it?
Oh, sorry. No, then it'd be the first.
Okay.
This one. Oops.
Okay, so a hydrocarbon has only hydrogen and carbon in it. Okay, so that is the definition of a hydrocarbon. Okay.
Mm-hmm.
Now this would be a derivative of the hydrocarbon because we added some oxygens.
For
Talk about that.
organic ones, do they include an H?
Can you repeat that, please?
For organic formulas things, do they include an H or a hydrogen, or is it?
Yeah, so organic compounds typically will have H's in them and they would have the carbons in them, right? So that's usually makes it an organic compound. Now, the carbon oxides aren't considered typically organic, but there are going to be a few of them that are going to be exceptions, okay?
Mhm.
Yeah, so this is considered an exception. And the funny thing is that if you talk to an organic chemist says they claim everything that has carbon in it for the most part. It's just that the inorganics, they need something to claim that has carbon in it every once in a while too. So.
Mhm.
Okay, so let's talk about hydrocarbons. Okay, so hydrocarbons are basically made up of hydrogens and carbons. So a alkane is a hydrocarbon that is saturated with hydrogens. Okay, now what I mean by saturated with hydrogens, we know that carbon can have 4 things attached to it. So if the carbon is attached to another carbon, and then it's going to be, all the remaining things are going to be attached to hydrogens. So it's going to occupy all 4 bonds. Like, let me give you an example of what I'm saying. Right? So if I have carbon attached to another carbon, I'm going to have 3 hydrogens coming off of each of those carbons. So this would be saturated because there's no double bonds or triple bonds. Okay, that's only single bonds. So a saturated hydrocarbon is one that has no double bonds or triple bonds. Okay, so saturated fats. So saturated fats would be fats that are only single bonds, no double bonds. Okay, unsaturated fat will have at least one double bond or triple bond. Okay.
Yeah.
Okay, so this is an example of an alkane because it's all single bonds. So A&E basically means that it's a single bond. All of the carbons are attached by single bonds. Okay, and everything that's attached to is single bonds. If it's an E&E, right, that means that we have a double bond, at least one double bond. So this is an example. Of a compound with a double bond. So we have a double bond between the 2 carbons, right? And so that's an alkene. Now, an alkane, an alkyne is one with a triple bond. So the compound has to have at least one triple bond between the carbons. Okay. Alkane, alkene, and alkyne. Okay. And if you take a look at it, 1, right, single bond, A, 2, E, and 3, Y. Okay, kind of helps us remember. Okay, so alkene, alkane, and alkyne. Okay, so are you guys good?
Yeah, and these are only for when it's hydrogen and carbon, right?
This is yes. So these are different types of hydrocarbons.
Okay.
Hold on one second. Let me stop this and fix this. Give me 1 second. Oops. That happens. It's crashing. Are you guys still there?
Yeah.
Okay, good, because my computer just at the front. Hold on, give me 1 second to figure out what's going on. There you go. Okay. Okay. Can you guys, oh, yes, can't see my screen. Sorry. My computer's old, and so it wants to do its own thing every once in a while. Okay, so, sorry, I have to put up what I had earlier. So when we talk about these alkenes, I mean these hydrocarbons, right? So alkanes, all single bonds, alkenes, at least one double bond, and then alkynes, at least one triple bond. Okay, we've talked about what we call saturated versus unsaturated, and then what we have also amphiphilic hydrocarbons, which basically means that they're in chains, right? And then aromatic, right? Aromatic basically means that they're going to have ring structures and they're going to have smells associated with it, like aroma, aromatic. Okay, amphiphatic, meaning that they're going to be kind of chained, and then the aromatic means that they're going to have a chain, it'll be a ring structure with double bonds in it. Okay, to give it an aroma type of smell. Okay, so we have the two divisions of hydrocarbons in addition to each of those different names. So now let's talk about how we're going to name these hydrocarbons, because with chemistry, we need to be able to start naming things. And that's what we're kind of building up to. And I like starting with organic chemistry because I think organic chemistry, nomenclature for organic chemistry is kind of more challenging. And then so when you guys start to name inorganic compounds, it gets a lot easier and you appreciate it that much more. Okay. So let's start with, we'll start off with the ones that we had written up here. I'll write them up again. So. Oops. And we're not going to get too in depth. We're just going to get some of the basics. So you guys will have some of the chemicals underneath your belt. So when you see them, like in our assignments, it'll be a lot easier to sit there and identify them and talk about them. Okay. So hydrocarbons are going to be named based upon the number of carbons that they have in them. Okay. And then we're going to go through the numbering system and then how we go about naming them in a second. Get these last ones up. And then I'm going to show you how to draw them a couple of ways. And then we're going to use a systematic way of drawing to make it a little bit easier for us so we don't have to keep track of all of the hydrogens. Okay, so the prefix meth means 1, eth is 2, prop is 3, bute is 4, pent is 5, hex is 6, hept is 7, oct is 8, non is 9, and dec is 10, Undec is 11. Dodec is 12. Okay. Are you guys with me so far? Okay, can you guys see those? Yeah. Okay. So I guess it's just you and me, Sam. So we're gonna go till about 11:35, and then we'll stop at that point. We'll stop a little early. Okay, so the thing that we want to do first when we're doing nomenclature, we want to find the longest carbon chain, and then we're going to use that to do our naming. So in this case, we only have 2 carbons, 1, 2. So then the prefix is going to be eth. So this guy would be called ethane because it's all single bonds between the 2 carbons. Okay. Now this guy has a double bond. So this guy would be called ethene. Okay. And then this guy would be called ethine. Okay. And this naming system is called Iupac Nomenclature. So when they ask you to name it using Iupac Nomenclature, you're going to use this system. It's also called the systematic. Nomenclature. Okay. Okay, so if I have 1, 2, 3, 4, 5 carbons, all single bonded. Okay, so 5 carbon chain, we would call this guy what?
Do you use the prefixes from over here, the pen?
That's right, we use this prefix and then we use ane at the end of it.
So pentane?
Pentane, that's right. Okay. Pretty simple?
Yeah.
Okay. So now let me show you another way of drawing it because it gets tiring writing all of those hydrogens, right? So another way that we write it, this guy would be called the expanded method, right? Showing where all the bonds are attached. Another way that we could write it is CH3, CH2, 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 CH3. Okay, so this would be called the condensed way of writing it, right? Although these numbers, I can't make subscripts on Zoom for some reason. So these would be subscript, okay? So, and the way that I like to write it is using the skeletal system, right? Skeletal system is just each point represents each vertice represents a carbon. So that's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. That would be the same thing as this and the same thing as this. Okay, so you would just count the number of points, 1, 2, 3, 4, 5. So that has 5 points. So then we would call this guy pentane. Okay, so this is called skeletal. And this guy would be called condensed. And it means exactly the same thing. Okay, so you'll see a lot of structures like this. We know that we're talking about carbon structures when you see symbols like this, where each of these represents a carbon. Do you see that? Okay. Okay, so now when we're talking about the double bond, I'm going to use the skeletal system since I like it so much. The way that we would draw a double bond is like this. So this would be 1 point. This would be where the double bond's at. So the double bond would start at the second carbon. So the double bond in this case would be between these 2 carbons here. Okay, and then let me get rid of one of these hydrogens. So the structure would look something like this. Okay, now, so in this case, because the double bond can be at any point on any of these carbons, we have to tell people where the double bond is going to be at, right? So when we go to name this guy, we want to try to make it so that the double bond has the lowest numbering system. So if we count the carbons, 1, 2, 3, 4, 5, right? So that tells us where each of the carbons is. We know that the double bond starts at the second carbon in this case, right? And we want to try to give it the lowest number because we can count from the other side. We could say that this was 1, 2, 3. But if we did that, that number would be a 3 instead of a 2. We want to try to give that double bond the lowest number possible. Okay, so we would name this guy. We have to say where the double bond starts at. So it would be 2, and then it was 5 carbon chain. What would be the prefix that we use for a 5 carbon chain?
Pent.
Pent. Okay, and then we put, it's a double bond, ene. Okay, so this guy would be called 2-pentene. So we're saying that on the second carbon, there is a double bond. Okay, you see that?
Yeah, sort of.
Okay, so I'm gonna draw another one. Let's say we have this. And the way that we draw a triple bond, because a triple bond is always going to end up being linear, is how it's made. So it's going to have something that looks like this. And then, so that's 1, 2, 3, 4, and then 5. Okay. So if we number the carbons, as I said, we can number it from either side. So we can say this is 1, this is 2, then this would be 3, this would be 4, and that would be 5. Or we can number it going the other way. The red numbers. So that's 1, 2, 3, 4, 5. So we would want to give the triple bond priority. So we want to give it the lowest number that we can give it. Okay. So would we use the red numbers or would we use the blue numbers?
The blue?
Blue or red? Blue or red?
Blue?
Nope,
No.
we're going to use the red numbers because if we use the red numbers, the double bond is going to start at the 2 and then at the 3. But if we use the blue numbers, the double bond is going to start at the 3. So we want to try to give it the lowest number that we can give it. So we're going to use the red numbers. Okay, so then if we go to name this, oops. So if we go to name this compound, it has 5 carbons. That's 1, 2, 3, 4, 5. So it has 5 carbons. So that would be a prefix of what?
Of pent.
Pent, again, okay. And then it has 1 triple bond. So then what is going to be the suffix?
Kyne, alkyne.
So it would be pent, and then we use the Y and E. We don't put the K. Yeah. So Y and E. So it'll be pentyne. Okay. Now we have to say where that triple bond is at. Triple bond is on the second carbon. So it'll be 2 pentyne. Okay.
Mm-hmm.
Do you see that?
Yeah. I'm still a
Okay.
little confused on the skeletal structure.
What was that?
It's still, the skeletal structure is a little confusing still.
Okay, so we'll work on that because that's usually what most people use as a skeletal structure, or they'll use something kind of in between the two, where they'll put some of the carbons but not all of them. Okay, so I'm gonna copy this real quick. Give me 1 second, and then we're gonna go to a whiteboard. That's the best way of doing this. Oops. Maybe. There we go. Let's see. Okay, so do you see my whiteboard?
Yeah.
Okay. So I'm going to draw a couple of structures up. even here. There we go. Okay, let's see. Okay, so let's go ahead and name this very first one. Call this A. This B. And this C. Okay, so let's count the carbons. So if we count the carbons, oops, wrong color. Okay, so that's 1, this is 2, this is 3, this is 4. So the prefix is going to be what?
But, I think, yeah.
Okay, so it's going to be, we call it bute.
Oh.
Okay, I know, but. Okay, so bute, and then the ending, since it's all single bonds.
What was it? Ane? Butane?
That's right, ane. So butane. Okay. Okay, this guy. So where are we going to want to start numbering from, first off, with B?
The right?
The right. Okay, so then that's 1, that's 2, that's 3, that's 4, that's 5, that's 6. Okay, so what would we call this guy?
Hex.
Okay. Okay, said hex. Oops. Okay, and the ending?
Ene?
Ene, that's right, hexene. Okay, now where is the double bond located at? Where does it start at?
At the one in between 1 and 2?
That's right, so we would say 1, hexene. And then this guy here. So where are we going to start counting from? The top or the bottom?
The bottom, I think.
There. So we'll slide 1, 2, 3, 4, 5, 6, 7, 8. Would that give me the lowest number where the triple bond is at?
No.
No, I wouldn't. So we don't want to start from the bottom. In this case, we'd want to start from the top.
Okay.
Okay, so starting from the top, that's 1, that's 2, that's 3, That's 4. That's 5. That's 6. That's 7. And that's 8. Okay. So what will be the prefix?
Oct.
Okay. Okay. And then the suffix?
Y and E.
Y and E. Okay. And where is that triple bond starting at?
1 and 3. Or
Are you
one?
sure? Because here, this is a single bond here.
2.
2. Yeah. Yeah, the triple bond is a little harder to see because how it's drawn, you know. But so we call this guy 2-octyne.
2 octine.
Okay.
Mm-hmm.
So how's that going? You got it?
Sort of.
Okay. Okay. So, well, and the homework assignments are going to be a couple of problems that are going to be dealing with this. So take a look. And this guy is chapter 21, I believe, in the textbook. So we're kind of skipping around. So.
Okay.
Okay.
Mm-hmm.
Okay. So I'm going to stop here today, and then I'll touch base with you guys. Well, Thursday's a holiday, so I won't see you guys during my office hours. So if you guys need anything, office hours on Friday, and then the lab will be on Friday.
Okay. Oh, sorry. I have a question. The lab from last week, I think it was. Do we still have to do that one, or?
Yes, you have to do it. I just haven't put up the instructions,
Okay.
the in-depth instructions. I'll be doing that today.
All right.
Yeah,
Thank you.
I end up spending my whole weekend at the hospital. So my sister ended up being at the hospital. So I haven't had a chance to do a lot of things. So
Sorry
I'm
about
working
that.
on it. It's been a rough semester, we'll put it like that.
Yeah, it has.
Yeah.
All right. Well,
Okay. I will see you guys this week. I mean, on Friday.
hopefully it gets better. Thank you.
Yeah, hopefully it does.
All right. Thank you. Have a nice day.
Okay. You too. Take care.